Hi class, this is the lecture for Friday, March 16th for the Section 2 COMHE 330 class on the case control studies. So let me get my computer set up. Make sure you guys are seeing what I'm seeing. It looks like it. All right, so in terms of housekeeping, I have posted the biweekly worksheet 3 key. I have not graded your biweekly worksheets yet, but I will hopefully do that tomorrow morning. If not tomorrow morning, then check for grades on Monday. In terms of the midterms, again, your midterm is going to be the 23rd, so next Friday, and the 25th. I'll provide a formula sheet that has been posted to Blackboard. Again, take a look at that formula sheet. Let me know if there's anything missing that you would like to see on there, and then I'll update it. But you need to let me know before next Friday, before I print everything and bring it to class. Right, so the first 30-ish slides of this lecture are a recap of the cohort lecture last week. And we did some of this on Tuesday, so I'm going to go through this pretty quickly. In terms of a confounder, again, you guys are thinking of confounding as a common cause. Remember, it's that third variable that's distorting our exposure-disease relationship. And specifically, it is a common cause, whereas a common effect is how you're identifying selection bias. So in a cohort study, we select participants on the basis of exposure, right? So we're starting with an exposed population, seeing how many cases develop in that exposed population. And we also have an unexposed population, and we're seeing how many cases develop in the unexposed populations. Now, today we're going to talk about a case control study, and in a case control study, you're actually starting with either cases, so people who have disease, or controls, people who do not have disease. So you're starting at a different point, right? With a cohort study, you're starting with exposure. With a case control study, you're starting with disease. So what's the difference between a cohort study and a randomized trial? Hopefully everyone's thinking randomization. In terms of how they are similar, remember we're comparing disease development among exposed and unexposed. So in both a cohort study and a trial, you have a simultaneous comparison. The big difference between them is the absence of randomization. So that means that confounding is still going to be a concern in a cohort study. We've already said this. I've already said this. We're selecting people for a cohort study on the basis of whether or not they're exposed. In terms of the types of cohort studies, we've talked about a prospective cohort study where we go through time with our cohort. We a priori set up the cohort and watch for cases of disease to develop. You're assigning exposure status on as your first step, then you're following them over time, and then you're assessing disease status. An example of a prospective cohort study would be the article that we read on Tuesday, where you're looking at the example here says red meat and colorectal cancer, but the article you read was looking at red meat as the exposure and mortality as the outcome. We also talked about retrospective cohort studies, and the distinction between retrospective and prospective cohort studies is that you are generally not going to have a pre-planned study, right? You're taking advantage of some database that already exists to assess, to define an exposed and an unexposed group and to look at their outcomes. So note that we're starting our study at a different point in time. I'm looking at this big blue block at the end. We are assigning, our first step is still the same. We're assigning people into this study based on exposure. And then we're assessing disease status. So we're not following them over time. The measure of association we use in a cohort study is going to be the relative risk ratio. So that is the ratio of risk of disease among the exposed compared to the risk of disease among the unexposed. You can also use an odds ratio, and I'm going to walk through an odds ratio today. We calculate the relative risk ratio by estimating the number of cases of disease. So A divided by A plus B, so the total number of exposed. That's going to be risk of disease in the exposed over risk of disease in the unexposed, and that would be C, the number of cases in the unexposed group, divided by the total number of people who do not have our exposure. And in terms of the interpretation, remember, we're always looking at the value of 1. So if we have a relative risk ratio of more than 1, that implies that the disease among the exposed is greater than among the unexposed. So there's a positive association. If we have a relative risk ratio of less than 1, it implies the rate of disease among the exposed is less than the unexposed. So you're saying there's a negative association, or whatever exposure you're talking about is actually protective. And you guys have seen this slide now a couple times. We are looking at family history as the exposure and the number of cases of incident depression that occur in this cohort. So the risk of disease, the risk of depression among my exposed group is 0.625. That's 50 divided by 80. The risk of disease among my unexposed group is going to be 0.25. That's 10 divided by 40. And the ratio of those two numbers, 0.625 divided by 0.25, is 2.5. So we would say that compared to persons without a family history of depression, so my unexposed arm down here, persons with a family history of depression were 2.5 times as likely to have depression. And just a note that you're going to want to know how to calculate and interpret a risk ratio for the midterm. In terms of potential biases in a cohort study, you are thinking of confounding as a bias because we're not randomizing people. Selection bias is a bias, and usually it will occur in the form of non-response or loss to follow-up. And you could also have some information bias. So this is going to be when the quality of the information you're obtaining is different for maybe your exposed or your unexposed arms. So we say we have selection bias when we observe an association, when in reality we observe an association between exposure and disease, when in reality there should not be an association between exposure and disease. And in cohort studies, we are often going to worry about selection bias due to what? Loss to follow-up. The other way you can think about selection bias is that we have selection bias when something is a common effect. So if the reason someone leaves the study, the cohort study, is because of their exposure, and also people are leaving the study because of the outcome, so because they're sick, then we can say that we have selection bias. And we talked about oral contraceptives and blood clots as a form of selection bias. So people leaving a study because they don't want to take oral contraceptives, and also leaving a study because they're sick because of blood clots. In terms of DAGs, remember you're thinking of confounders as common causes and selection bias as a common effect. The rules of a DAG are that the exposure always has to go to the outcome, and you only have one arrowhead, right, for all the causal mechanisms you're trying to identify. You can think of age, race, gender, any of your proxies for socioeconomic status, education, income as confounders, usually. They're almost always going to be confounders. If we were drawing the DAG for red meat and colorectal cancer, which we did, you could obviously draw that a million different ways. Here is one example. where we have identified healthy lifestyle, age, and income as confounders of the exposure outcome relationship. So as confounders of the association between red meat consumption and colorectal cancer. And remember, if we were doing this in a trial, you wouldn't have any confounders, right? Because you should have balance on all our measured and unmeasured confounders if you could randomize people to some sort of intervention where you make them eat meat, which obviously we wouldn't do. But if you could, then you wouldn't have to worry about confounding. Okay, so today we're going to be talking about case control studies and some of the biases in case control studies. And specifically, you should be able to answer these questions by the end of this lecture. So the types of biases we're going to worry about in a case control study, what are they? What is the measure of association we use for a case control study and why? And why can't we use a case control study to estimate incidence or prevalence? Okay, so in a case control study, we define our study on the basis of disease status, right? So subjects get picked. The first step in a case control study is that subjects get picked on the basis of their outcome. So this is different from a cohort study because in a cohort study, we're picking people on the basis of exposure. Here, in a case control study, we're picking people on the basis of their outcome. In a cohort study, we start by selecting exposed and unexposed. So we start with exposure instead of outcome. In a case control study, we start with the outcome. And the tricky part in a case control study is going to be identifying the controls. And what I want you to get used to thinking is that we want our controls to be similar to the cases in all aspects except for disease status. So except for the fact that one group has the disease we're interested in and the other group does not. Case control studies are going to use a retrospective approach to collect data. So that means that we're enrolling people as a case of disease or as a control. So we already know disease status, and then you're going to ask them about their exposures that happened in the past. So when I say retrospective here, this refers to collecting information on exposures that have happened in the past. All right, so let's look at our diagram for a case control study. Note that our blue box is present day. So we do not need to follow people over time, right? We know if they have disease or if they don't. So step one in a case control study is going to be assign people as either cases or controls. Then I'm going to ask them about their exposures that happened in the past. So I'm going to ask my cases if they have exposures. Were they smokers, if that's what we're studying? And I'm going to ask my controls, were you a smoker? In terms of comparing a retrospective case control study to a retrospective cohort study, in a case control study, we know disease status, right? So we have questions about exposure status. That's what we're asking people. And in a retrospective cohort study, we know the exposure status. That means these two studies are retrospective in different ways. So in a cohort study, we're going to use data that was collected in the past. In a case control study, we're using data that was collected in the present, but it refers to the past. So I'm asking people today about exposures that maybe happened 10 years ago. Whereas in a retrospective cohort study, that data from 10 years ago was already collected. All right, so here's a reminder of our retrospective cohort figure. And now note that the question marks have moved, right? Because we're starting our study at the same point in time, but we assign people on the basis of exposure, right? Our first step has changed. So in a case control study, our first step was to assign people on the basis of disease status. But in a cohort, our first step is to assign people on the basis of exposure status. And then we're asking people in a cohort study. So step 1, assign people according to exposure status. Step 2, find out about disease status. Okay. In the 1940s, Norman Gregg notices that there is a high number of children presenting with an unusual form of cataract. And he noted that many of these children had been in utero during a rubella outbreak. So Norman Gregg hypothesizes that prenatal rubella exposure results in the development of cataracts in infants. If we wanted to test this hypothesis using a case-controlled design, what would we do? Well, first, we'd start by identifying children with cataracts, right? And then we're also going to want to identify some children without cataracts, our controls. And then we're going to need to find out, how many of them were exposed to rubella in utero. So we're probably going to ask their moms, right? We identify children that have cataracts, those are our cases, and then we're going to ask their moms if they had rubella. And we're going to do the same thing with the controls, the children without cataracts. We're going to ask their moms if they had rubella. And then we're going to compare the level of exposure in our cases to the level of exposure in our controls. And if the exposure is associated with the disease, you would expect to see a higher proportion of cases. So a higher proportion of children with cataracts, you would expect to see a higher number of their mothers reporting that they had rubella. Compared to the children without cataracts, you would expect to see a lower number of their mothers reporting that they had rubella. So again, what I want you to note here is that in a case control study, we are comparing the proportion with the exposure, whereas in a cohort and also in trials, we're comparing the number of people who develop the disease. So case control, we're comparing the number of people with the exposure. In cohorts and trials, we're comparing the number of people with the disease. That's because in a case control study, we start by knowing disease status, and then we're measuring exposure status. The measure of association that we're going to use in a case control study is called an odds ratio. And an odds ratio is when I'm looking at the frequency of the exposure, the odds of the exposure among the cases, compared to the odds of exposure among the controls. So once again, what we're doing with a case control study is comparing exposures among the cases to exposure among the controls. So let's walk through how we calculate this. All right, this is what I might be calling Formula 1 here. So first, to calculate the odds of exposures among the cases, right, and my cases are going to be cells A and cells C, I would divide A by C. That would give me the odds of exposure among my cases. Now, I'd also need to calculate the odds of exposure among my controls. So that would be B divided by D. And I'm going to take the ratio of those two. So A divided by C divided by B divided by D. And that resolves to AD over BC. So odds of exposure among the cases, A over C, odds of exposure among the controls, B over D, and the ratio. And you're interpreting an odds ratio in the same way that you interpret a risk ratio. In terms of the reference value of 1. So if we have an odds ratio of more than 1, it implies that there's a positive association between the exposure and the disease. If we have an odds ratio of less than 1, that implies that your exposure might be protective, that there's a negative association. And if we have an odds ratio equivalent to 1, that means there's no association between the exposure and disease. Now, I just had us calculate the odds of exposure. And a nice thing that happens with an odds ratio is that the odds of exposure is going to be equivalent to the odds of disease. So this was Formula 1, where we were calculating odds of exposure. Now we're going to look at Formula 2, where we calculate odds of disease. So Formula 1, odds of exposure. Formula 2, odds of disease. Now, if I asked you to calculate the odds of disease among the exposed, you would take A divided by B. And if I asked you to calculate the odds of disease among the unexposed, you would take C divided by D. So that means odds of disease among the exposed, A over B. Odds of disease among the unexposed, C over D. And to calculate the ratio, I would have A divided by B divided by C divided by D, which resolves to AD over BC. So it's resolving to the same thing. Formula 2, we end up with AD over BC. And in Formula 1, you also end up with the same thing, AD over BC. All right, so that's why we can say that odds of exposure is equivalent to the odds of disease. So a nice thing that happens with an odds ratio is even though in a case control study, we are measuring exposure status, right? I know who my cases are, I know who my controls are. I can interpret my odds ratio where we've measured exposure status as the odds of disease. So in this example, and this is fake data, I have cases, this is children with cataracts, and I have controls, this is going to be infants born without cataracts, and I've asked all their mothers if they had rubella. So odds of exposure among my cases would be 50 divided by 10, or 5, A over C. Odds of exposure among my controls would be 30 divided by 30, B over D, or 1, which means that I end up with an odds ratio of 5. So that was Formula 1, odds of exposure. Now Formula 2, odds of disease. Exact same data, but if I calculate the odds ratio, A divided by B, 50 over 30, I'm going to end up with 5/3. And the odds, did I just say odds of exposure about A over B? Sorry, guys. I mean odds of disease. So A over B is odds of disease. I wish I could go back and delete that from the recording. But A over B, odds of disease. Among my exposed, C over D, odds of disease among the unexposed. And that would be 10 divided by 30, or 1/3. And what I want you guys to see here is that we end up with the same odds ratio, right? We have 5 here. Our odds ratio is 5. So Formula 1, where we are using the odds of exposure, we have an odds ratio of 5. Formula 2, where we're calculating the odds of disease, we also end up with an odds ratio of 5. Okay, so using Formula 1, we're calculating odds of exposure. We could say that compared to infants without cataracts, so our controls, infants with cataracts had 5 times the odds of exposure to rubella. We could also say, using Formula 2, odds of disease, that compared to infants without in utero rubella exposure, the unexposed, infants who were exposed to rubella in utero had 5 times the odds of having cataract. So note that we can interpret the odds ratio as the odds of disease because the equations are equivalent. And that's what you're going to see a lot of times with the case control study, is that people interpret an odds ratio as the odds of disease because that makes more sense, right? You want to know if the exposure is associated with an increased odds of disease. Even though in a case control study, what you're measuring, what you're trying to find out is whether or not people had an exposure, because you know their disease status. But people will interpret an odds ratio as the odds of disease because it is equivalent to the odds of exposure. Now, the important thing to note here is that odds are not the same thing as risk or likelihood or probability. That means that you wouldn't want to say that compared to infants without in utero rubella exposure, infants who were exposed to rubella in utero had 5 times the risk, we're not talking about risk here. Now we're talking about odds. Remember, when we talk about risk, we are talking about likelihood and probability, and that's not what we've calculated here. So that means that odds ratios are a little hard to interpret. So when I say that someone has 5 times greater odds, it's not as intuitive as me saying 5 times greater risk. So a disadvantage of a case control study is that it is an indirect estimate of risk. Okay, so we cannot estimate prevalence or incidence in a case control study. And the reason why we cannot do that is because we get to pick the number of cases and controls in the study. So let's say I have 60 cataract cases and I want to enroll, for every 1 case, I'm going to enroll 1 control. So I'm going to have 60 non-cataract cases. That means that my prevalence is 50%, right? I have created a study where the prevalence is 50%. And this is one of the reasons why we can't estimate the likelihood of disease or the risk of disease or a risk ratio because I get to pick the number of cases and the number of controls. So I'm always setting the prevalence in my study. If I wanted to enroll if I wanted to enroll 2 controls for every 1 case, that would mean my 2 controls for every 1 case means that 1 in 3 of the people enrolled in my study have the disease, or the prevalence is 33%. I set the disease prevalence in a study, so I cannot measure the risk of disease in a case control study, which also means that I cannot measure a risk or report a risk ratio. Selection bias is going to be one of the biggest sources of concern in a case control study. And in fact, it's one of the reasons case control studies have sort of fallen out of favor. And we can have selection bias either as a result of how we've selected our cases or as a result of how we've selected our controls. So things to keep in mind when you're selecting cases. 1, exposures that you identify may actually just be unique to a hospital or a referral pattern, right? If I show up at a hospital, it is probably because of my insurance. And that means that people who are also going to that hospital or who are being referred to that hospital might have similar exposures as me. For that reason, it's often going to be desirable to select cases from many hospitals. So not just 1 hospital, you're going to try to get cases from 5 or 6 hospitals around the city. You also need to decide if you want incident or, hold on. Oh, wait, it looks like it's the same on your screen. Sorry, on my screen it's moved away. How do I go back into presentation mode? Set up slideshow, browsed by an individual. Okay. Is that still the same? Oh no. Hold on. Sorry, class. Escape. All right, what are you seeing now? Nothing. Now I think you are seeing a picture of my sister and I application window. Oh no. All right, guys, I might have to stop here and start another one when I figure out what I've done wrong. Yep, that's what I'm going to have to do. So you guys are going to have two parts to this lecture.